application of molecular symmetry and group theory, we will learn about the formation of molecular orbitals of various molecules such as BRF5, BF3 and CCl4. Now let us take first the construction of molecular orbital of BRF5. For doing this, the various steps involved are: first find out the point group. The point group of this BRF5 is C4V. Then we look the central atom. The central atom over here is bromine, and we look for the valence electron of this bromine atom. And valence electron are 1s orbital and 3p orbital. Now we look the symmetries of the atomic orbitals of various orbitals, which are given as S belongs to A1, Px belongs to this, and Py belongs to this, and Pz belongs to this. Similarly, we look the symmetry of d orbitals. Now, these are shown in this model as such. This one is shown as the R5, then we are having R2, R4, R1 and R3 as shown. This is your BRF5 molecule, and we will take these BRF5 molecules and will see the effect of various symmetry operation on these bond vectors. And we will see now how many bond vectors are shifted and how many bond vectors are not shifted. A bond vector which is shifted on performing symmetry operation will contribute character is equal to 0 to the reducible representation. A bond vector which is not shifted will contribute chi is equal to +1 to the reducible representation, and a bond vector which is unshifted but its direction is reversed, it will contribute -1. With this, we will take now the various symmetry operation and find out how many atoms are shifted. Let us take now first E operation on this molecule. There are 5 atoms. E means doing nothing. I do not rotate on this. Now, what I find, all the 5 vectors are not shifted. Now, if I take C4 axis, C4 axis means along this axis, and if I give 90-degree rotation, all the 4 vectors in the plane are shifted, and only this R5 is not shifted because it lies along your C4 axis. Now, if I take sigma V containing 2 of the bond vectors like this, one passing and then another passing through then this. So, if I take sigma V, 3 bond vectors will not be shifted. Now, let us take sigma D. Sigma D means a plane containing this R5 and bisecting the other 2 bond vectors, angle made by bond vectors. It means all the 4 bond vectors in the plane are shifted and this R5 is not shifted. Similarly, if we take C2 along C4 axis, here what will happen? If I perform 180-degree rotation, this atom will go to this atom on performing this rotation. It means again all the 4 vectors into the plane are shifted and the 5th vector which lies into C2 axis is not shifted. So, like this we are having this summary of this unshifted vector 5, 1, 1, 3, 1, and again this is multiplied with our the multiplication factor, and we get this reducible representation as 51131, and this can be reduced by making use of the standard reduction formula, and later on we can make use of this is we are getting the reduction result, and after making use of the projection operator method we can find out the SALC of LGOs corresponding to the 5 orbitals. Now, next step will be we take the valence electron on the bromine on the left hand side, that is on this side over here, and valence electron of LGOs of 5 fluorines on the right hand side, and we match them, and then we draw the MO diagram of this molecule, and filling of the electrons in these MO diagrams is in a similar manner as we follow in the atomic orbital. So, this gives us the MO diagram of BRF5 molecule.
Let us now start with the formation of molecular orbitals by taking few examples. The first example taken into consideration is molecular orbital for BRF5 C4V molecule. As we are already aware of sigma bonding hybridization for this molecule. In this molecule, we will discuss formation of molecular orbital and energy level diagram for the same. Following the various steps, that are step 1, point group the molecule is C4V, and step 2, central atom is bromine. Bromine has valence electronic configuration AR 3D10 4s2 4p5. Thus the valence atomic orbitals are 1s orbital and 3p orbitals, that is 4. The symmetries of these atomic orbitals under C4V symmetries can be obtained from character table of C4V point group, and these are as given. Continuing with the steps, the step third is the structure and various bone vectors in BRF5, which are as shown in the figure. The effects of symmetry operations of C4V point group on BRF vectors R1, R2, R3, R4, and R5 are as shown in figure. Moving on, the results of symmetry operations of C4V point group on BRF bone vector is as summarized in table. The vector which is unshifted contributes character +1. The vector which is shifted contributes character 0. The vector which is unshifted but only direction is reversed contributes character -1. Tau BRF can be reduced by standard reduction formula as tau BRF is equals to 2A1 plus B1 plus E. It means ligand group orbitals must be of A1 and B1 and E type. Step 4 says that using projection operators corresponding to two A1, B1, E, that is A1O, B1O, and EO on R1, R2, R3, R4, and R5 orbital functions can get SALC of ligand group orbitals, that is 5f orbitals fragment. Using ligand group orbital of A1 and B1 and E-type of F5 fragment on the right-hand side of the molecular orbital diagram and symmetry of the S and P atomic orbitals of bromine atom on the left-hand side and matching the symmetry and taking energy into consideration, the molecular orbital diagram for BrF5 molecule may be constructed as shown in the figure.
Now, a similar procedure can be discussed in the construction of BF3 molecule. We take the BF3 molecules and we find the point group for this molecule. You have learned in the earlier modules it contains a C3 axis and there are three C2 axes, one along this, another along this, another along this, and it has a sigma H in it. So, the molecule belongs to D3H point group. Now, again we have three bond vectors into this R1, R2 and R3, and we will similarly use this. This is the, we are having the bond vectors R1, R2 and R3 in these molecules, and this is C3 axis is shown. And also now we find the valence electron of this boron atom and find their symmetries, and these symmetries are given as A1 dash, E, E dash and A2 double dash. These symmetries are given, and now let us find out the symmetries of the fluorine atoms, and for that we have to see the effect of various symmetry operations on R1, R2 and R3. Now, I have shown over here the effect of the various symmetry operation on these vectors. Let us take the effect of C2 axis or sigma V. That is, if this is the molecule, this is my C2 axis, this is my C2 axis, and this is also sigma V along this. So, what doing by this, what I am getting? Only this bond vector is not shifted. These two bond vectors, this and this, they are shifted, and only one bond vector is not shifted. Now, let us take sigma H. Sigma H means the plane of the molecule as it lies on my palm, and it means all the three atoms, this, they are not shifted. How many bond vectors are not shifted? 1, 2 and 3. Here I am taking bond vectors, not atoms. So, 3 bond vectors are not shifted. Let us take C3 axis which passes perpendicular to this plane. So, if I give a rotation along this like this 120-degree rotation, what happens? This bond vector, this bond vectors, this bond vector, they interchange, all are 3 shifted. So, like this we find the number of bond vectors shifted by performing the various symmetry operation of the molecules, and these are shown over here. And I go for the multiplication factor for this, and after that I get this is the reducible representation, and this reducible representation can be reduced to irreducible representation by following standard reduction formula, and the results are given slide, that is A1 dash and E1 dash. So, these are the symmetries of the logos of fluorine atoms, and the orbitals are shown by the lowercase numbers. These are the symmetries and these are the orbitals of the logos of bromine. So, we have now with us the valence electron symmetry of the boron atom and the symmetry of the LGOs of fluorine atom, and we try to match both On this left hand side we are having symmetry of boron, and on this we are having symmetry of the LGOs of fluorine, and they are matched, and after matching we get the bonding and anti-bonding MOs, and these are filled as per the rules we are following in atomic structure. Now, after this, let us take another example, though it is very symmetrical, and let us try to find out the MO diagram for this molecule. For this, I will take the example of.
Let us now continue with the same procedure, that is, step 1 is the point group of the BF3 is D3H, and the step 2 is that the symmetries of atomic orbitals of boron in D3H can be read from the character table of D3H point group. The character table is as shown. The symmetries of the atomic orbital of boron are as shown. The step 3 is the structure and bone vectors in BF3, which is as shown. Similarly, the effect of symmetry operations on D3H point group on the three BF bone vectors is as shown in the figure. Finally, the results of symmetry operations of D3H point group on BF bone vectors is as summarized in the table. The vector which is unshifted contributes character +1. The vector which is shifted contributes character 0. The vector which is unshifted but only direction is reversed contributes character -1. Now, tau BF can be reduced to tau BF is equals to A1 dash plus E dash. It means that the fragment F3 of three pendant fluorines have the symmetry of A1 dash plus E dash. Thus, these ligand group orbital are of type A1 dash and E dash type of orbitals. 1s orbital in boron is completely filled up, and it will not be considered for qualitative molecular orbital formation of BF3 molecule. The 2s orbitals in boron and 2p orbitals are used in molecular orbital formation. Lastly, using ligand group orbital of A1 dash and E dash type on the right hand side of the diagram and symmetry of the atomic orbitals of the boron atom on the left hand side, and matching the symmetry and taking into energy consideration, the molecular orbital diagram for boron trifluoride molecule has been constructed as shown in figure.
CCl4. CCl4 is a molecule like this, as I have shown over here. Black one is carbon, and all these are chlorine atom, as I am showing over here. Now, this molecule belongs to tetrahedral point group. It has C3 axis. How many? 4 C3 axis it has into this, each along this bond. Now, again I will follow the same procedure as we have discussed in the case of BRF5 and BF3. First step, we will just know the valence electron of the carbon, and then we will find out the symmetry of LGOs of chlorine, and these are again shown over here. These are the symmetry of S, Px, Py, Pz orbitals, dxy, dyz and dz orbitals of the valence electrons of the carbon. And here in this, the tetrahedron is placed inscribed into a cube. And again I have numbered these R1, R2, R3, that is this one, as the bond vectors, and we will see the effect of symmetry operations corresponding to the molecule and see the effect of on these bond vectors. And here this table shows the effect of bond vectors. These are the unshifted vector. E means there are 4 bond vectors, this one, this one, this one, this. All are unshifted. If I go for the C3 rotation like this, only one bond vector which is along which the rotation is carried out is unshifted. Now let us take C2 axis. How to see the C2 axis into this molecule? Let us put the molecule in this manner. And here it is one angle and below is also one angle. So this is my C2 axis which passes through this molecule and we can rotate it through this. So by following C2 axis, all bond vectors are shifted. Now similarly S4 axis, because S4 axis lies along C2 axis, again it will give the all bond vectors are shifted. If I take sigma d that is it contains 2 of the vectors and bisects the angles between other 2 vectors. So what happens into this? Only 2 bond vectors are not shifted. So like this the results are as over here. In this I am having 4, 1, 0, 0, 2. These are multiplied by the multiplication factors to give me the result 4, 1, 0, 0, 1, and this can be reduced to A1 and T2. So these are the symmetries of the LGOs of chlorine, that is chlorine LGOs belong to A1 and T2 symmetry, belong to A1. Now again following the same rule, that is we take the symmetries of the valence electron on the left hand side and the symmetries of the LGOs on the right hand side and match these LGO orbitals and the valence orbitals of right symmetry and right energy, and we get the MO diagram in this manner, and the electrons are filled up again as per the rules we follow in for atomic orbitals.
Applying the same procedure for construction of molecular orbital for CCl4 molecule, let us do step 1. That is, the point group of the molecule is TD, and step 2 is symmetries of atomic orbitals of carbon atom is given by the character table of TD point group as shown. The symmetries of atomic orbitals of carbon are as shown, and the structure and 4 CCl bone vectors in CCl4 are as shown in figure. The effects of symmetry operations on these 4 CCl bone vectors are as summarized in the table, and tau r can be reduced to irreducible representations by the standard formula, and the results are tau r is equals to A1 plus T2. It means ligand group orbital of Cl4 fragment involving CCl bond only are of A1 and T2 type. As 1s orbital in carbon is completely filled up and it will not be considered for qualitative molecular orbital formation of CCl4 molecule. The 2s orbital in carbon and 2p orbitals are used in molecular orbital formation. Using ligand group orbital of A1 and T2 type on the right hand side of the diagram and symmetry of the atomic orbitals of carbon atom on left hand side and matching the symmetry and taking into energy consideration. Using ligand group orbital of A1 and T2 type on the right hand side of the diagram and symmetry of the atomic orbitals of carbon atom on left hand side and matching the symmetry and taking into energy consideration, the molecular orbital diagram for carbon tetrachloride molecule may be constructed as shown in figure. The d orbitals, which are also of right symmetry for bond formation, have also been included in molecular orbital scheme for CCl4 molecule. Following table gives the type of atomic orbitals at the central atom involving sigma and pi bonding molecular orbital formation.
So, in this module we have found out the formation of the various MO diagrams of the BRF3, BRF, BRF5, BA, boron trifluoride and then CCCl4s. Now, this table gives me some of the symmetries of the various atomic orbitals which are nearly involved in sigma bonding in this and pi bonding. So, in summary, what we have looked, you have in this model you have learnt how to construct molecular orbitals for various molecules just by knowing how many bond vectors are shifted during the symmetry operations, and after that we go for the irreducible representations, and that give us the type of orbitals of LGOs of the ligands are involved. So, by matching the valence atomic orbitals and atomic orbitals of LGOs, we can get the molecular orbital diagram of the molecule.